What is up, everybody? In today's video, we're going to go from the paper on deep deterministic policy gradients all the way into a functional implementation in Tensorflow. So you're going to see how to go from a paper to a real-world implementation all in one video. Grab a snack, a drink, because this is going to take a while. Let's get started. So the first step in my process really isn't anything special. I just read the entirety of the paper, of course starting with the abstract. The abstract tells you what the paper is about at a high level. It's just kind of an executive summary. Introduction is where the authors will pay homage to other work in the field, kind of set the stage for what is going to be presented in the paper as well as the need for it. The background kind of expands on that, and you can see here it gives us a little bit of mathematical equations. And you will get a lot of useful information here. This won't talk too much about useful nuggets on implementation, but it does set the stage for the mathematics you're going to be implementing, which is of course critical for any deep learning, or in this case deep reinforcement learning, paper implementation. The algorithm is really where all the meat of the problem is. It is in here that they lay out the exact steps you need to take to implement the algorithm, right? That's why it's titled that way. So this is the section we want to read most carefully. And then of course they will typically give a table where they outline the actual algorithm. And oftentimes if I'm in a hurry, I will just jump to this because I've done this enough times that I can read this, what is called pseudocode. If you're not familiar with that, pseudocode is just an English representation of computer code. So we will typically use that when we outline a problem, and it's often used in papers, of course. So typically I'll start here reading it and then work backward by reading through the paper to see what I missed. But of course it talks about the performance across a whole host of environments, and of course all of these have in common that they are continuous control. So what that means is that the action space is a vector whose elements can vary on a continuous real number line instead of having discrete actions of 0, 1, 2, 3, 4, or 5. So that is the really motivation behind deep deterministic policy gradients, is that it allows us to use deep reinforcement learning to tackle these types of problems. And in today's video, we're going to go ahead and tackle the, I guess, pendulum swing up, also called the pendulum problem. Reason being is that while it would be awesome to start out with something like the bipedal walker, you never want to start out with maximum complexity. You always want to start out with something very, very small and then scale your way up. And the reason is that you're going to make mistakes, and it's most easy to debug, most quick to debug, very simple environments that execute very quickly. So the pendulum problem only has, I think, 3 elements in its state vector and only a single action. So, or maybe it's 2 actions, I forget. But either way, it's a very small problem relative to something like the bipedal walker or many of the other environments. You could also use the continuous version of the cart pole or something like that. That would be perfectly fine. I've just chosen the pendulum for this particular video because we haven't done it before. So it's in here that they give a bunch of plots of all of the performance of their algorithm with the various sets of constraints placed upon it and different implementations, so you can get an idea. And one thing you notice right away, it's always important to look at plots because they give you a lot of information visually, right? It's much easier to gather information from plots than it is text. You see that right away they have a scale of 1. So that's telling you its relative performance, and you have to read the paper to know relative to what. I don't like that particular approach. They have similar data in a table form, and in here you see a whole bunch of environments they used, and there's a broad variety. They wanted to show that the algorithm has a wide arena of applicability, which is a typical technique in papers. They want to show that this is relevant, right? If they only showed a single environment, people reading it would say, well, that's all well and good, you can solve one environment, but what about these dozen other environments? Right? And part of the motivation behind reinforcement learning is generality. Can we model real learning in biological systems such that it mimics the generality of biological learning? One thing you notice right away is that these numbers are not actual scores. So that's one thing I kind of take note of and causes me to raise an eyebrow. So you have to wonder the motivation behind that. Why would the authors express scores in a ratio? There's a couple different reasons. One is because they want to just to make all the numbers look uniform. Maybe the people reading the paper wouldn't be familiar with each of these environments, so they don't know what a good score is, and that's a perfectly valid reason. Another possibility is they want to hide poor performance. I don't think that's going on here, but it does make me raise my eyebrow whenever I see it. The one exception is the Torx, which is a totally open race car simulator environment. I don't know if we'll get to that on this channel. That would be a pretty cool project, but that would take me a few weeks to get through. But right away you notice that they have a whole bunch of environments. These scores are all relative to 1, and 1 is the score that the agent gets on a planning algorithm, which they also detail later on. So those are the results, and they talk more about, I don't think we saw the headline, but they talk about related work, which talks about other algorithms that are similar and their shortcomings, right? They don't ever want to talk up other algorithms. You always want to talk up your own algorithm to make yourself sound good. Why else would you be writing a paper in the first place? And of course, a conclusion to tie everything together. References. I don't usually go deep into references. If there is something that I feel I really, really need to know, I may look at a reference, but I don't typically bother with them. If you were a PhD student, then it would behoove you to go into the references because you must be an absolute expert on the topic. And for us, we're just, hobbyists. I'm a YouTuber, so I don't go into too much depth with the background information. And the next most important bit of the paper are the experimental details, and it is in here that it gives us the parameters and architectures for the networks. So this is where, if you saw my previous video where I did the implementation of DDPG and PyTorch in the continuous lunar lander environment, this is where I got most of this stuff. It was almost identical with a little bit of tweaking. I left out some stuff from this paper, but pretty much all of it came from here. In particular, the hidden layer sizes, 400 and 300 units, as well as the initialization of the parameters from a uniform distribution of the given ranges. So just to recap, this was a really quick overview of the paper, just showing my process of what I look at. The most important parts are the details of the algorithm as well as the experimental details. So as you read the paper, like I said, I gloss over the introduction because I kind of already understand the motivation behind it. I get the idea. It basically tells us that you can't really handle continuous action spaces with deep Q networks. We already know that. And it says, you can discretize the state space, but then you end up with really, really huge actions. Sorry, you can discretize the action space, but then you end up with a whole boatload of actions. What is it? 2,187 actions. So it's intractable anyway. And they say what we present, a model-free off-policy algorithm. And then it comes down to this section where it says the network is trained off-policy with samples from a replay buffer to minimize correlations. Very good. And train with the target Q network to give consistent targets during temporal difference backups. So in this work we make use of the same ideas along with batch normalization. So this is a key chunk of text, and this is why you want to read the whole paper, because sometimes they'll embed stuff in there that you may not otherwise catch. So as I'm reading the paper, what I do is I take notes, and you can do this in paper, you can do it in text document. In this case, we're going to use the editor so that way I can show you what's going on, and it's a natural place to put this stuff because that's where you're going to implement the code anyway. Let's hop over to the editor and you'll see what I take notes. So right off the bat, we always want to be thinking in terms of what sort of classes and functions will we need to implement this algorithm. So the paper mentioned a replay buffer as well as a target Q network. So the target Q network, for now, we don't really know what it's going to be, but we can write it down. So we'll say we'll need a replay buffer class and need a class for a target Q network. Now, I would assume that if you're going to be implementing a paper of this advanced difficulty, you'd already be familiar with Q-learning, where you know that the target network is just another instance of a generalized network. The difference between the target and evaluation networks are the way in which you update their weights. So right off the bat, we know that we're going to have a single class, at least one. If you know something about actor-critic methods, you'll know that you'll probably have two different classes, one for an actor, one for a critic, because those two architectures are generally a little bit different. But what do we know about Q networks? We know that Q networks are state action value functions, right? They're not just value functions. So the critic in the actor-critic methods is just a state value function in general, whereas here we have a Q network, which is going to be a function of the state and action. So we know that it's a function of S and A. So we know right off the bat it's not the same as a critic. It's a little bit different. And it also said we will use batch norm. So batch normalization is just a way of normalizing inputs to prevent divergence in a model. I think it was discovered in 2015, 2014, something like that. So then we use that. So we'll need that in our network. So we know, at least right off the bat, a little bit of an idea of what the network is going to look like. So let's go back to the paper and see what other little bits of information we can glean from the text before we take a look at the algorithm. Reading along, we can say blah blah. They say a key feature is simplicity. It requires only a straightforward actor-critic architecture and very few moving parts. And then they talk it up and say it can learn policies that exceed the performance of the planner, the planning algorithm, even learning from pixels, which we won't get to in this particular implementation. So then, okay, no real other nuggets there. The background talks about the mathematical structure of the algorithm. So this is really important if you want to have a really deep, in-depth knowledge of the topic. If you already know enough about the background, you would know that, the formula for discounted future rewards, you should know that if you've done a whole bunch of reinforcement learning algorithms. If you haven't, then definitely read through this section to get the full idea of the background and the motivation behind the mathematics. Other thing to note is it says the action value function is used in many algorithms. We know that from deep Q learning. And then it talks about the recursive relationship known as the Bellman equation. That is known as well. Other thing to note, what's interesting here, and this is the next nugget, is if the target policy is deterministic, we can describe it as a function mu. And so you see that in the remainder of the paper, like in the algorithm, they do indeed make use of this parameter mu. So that tells us right off the bat that our policy is going to be deterministic. Now, if you could probably guess that from the title, right? Deep deterministic policy gradients, right? So you would guess from the name that the policy is deterministic. But what does that mean exactly? So a stochastic policy is one in which the software maps the probability of taking an action to a given state. So you input a set of state and out comes a probability of selecting an action, and you select an action according to that probability distribution. So that right away bakes in a solution to the explore-exploit dilemma so long as all probabilities are finite, right? So as long as a probability of taking an action for all states doesn't go to zero, there is some element of exploration involved in that algorithm. Q-learning handles the explore-exploit dilemma by using epsilon greedy action selection, where you have a random parameter that tells you how often to select a random a random action, and then you select a greedy action the remainder of the time. Of course, policy gradients don't work that way. They typically use a stochastic policy, but in this case we have a deterministic policy. So you have to wonder right away, okay, we have a deterministic policy. How are we going to handle the explore-exploit dilemma? So let's go back to our text editor and make a note of that. So we just want to say that the policy is deterministic. How to handle explore-exploit. And that's a critical question, right? Because if you only take what are perceived as the greedy actions, you never get a really good coverage of the parameter space of the problem, and you're going to converge on a suboptimal strategy. So this is a critical question we have to answer in the paper. So let's head back to the paper and see how they handle it. So we're back in the paper, and you can see the reason they introduced that deterministic policy is to avoid an inner expectation, or maybe that's just a byproduct. I guess it's not accurate to say that's the reason they do it. But what's neat is it says the expectation depends only on the environment. It means it's possible to learn Q to the mu, meaning Q is a function of mu, off policy, using transitions which are generated from a different stochastic policy beta. So right there we have off policy learning, which is say explicitly with a stochastic policy. So we are actually going to have two different policies in this case. So then this already answers the question of how we go from a deterministic policy to solving the explore-exploit dilemma, and the reason is that we're using a stochastic policy to learn the greedy policy, or a purely deterministic policy. And of course they talk about the parallels with Q-learning because there are many between the two algorithms. and you get to the loss function, which is of course critical to the algorithm, and this y of t parameter. Then of course they talk about what Q-learning has been used for. They make mention of deep neural networks, which is of course what we're going to be using. That's where the deep comes from, and talks about the Atari games, which we've talked about on this channel as well. And importantly, they say the two changes that they introduce in Q-learning, which is the concept of the replay buffer and the target network, which of course they already mentioned before. They're just reiterating and reinforcing what they said. That's why we want to read the introduction and background type material to get a solid idea of what's going to happen. So now we get to the algorithmic portion, and this is where all of the magic happens. So they again reiterate that it's not possible to apply Q-learning to continuous action spaces because, reasons, right? It's pretty obvious. You have an infinite number of actions. That's a problem. And then they talk about the deterministic policy gradient algorithm, which we're not going to go too deep into, right? For this video, we don't want to do a full thesis. We don't want to do a full doctoral dissertation on the field. We just want to know how to implement it and get moving. So this goes through and gives you an update for the gradient of this parameter j, and gives it in terms of the gradient of q, which is the state action value function, and the gradient of the policy, the deterministic policy mu. Other thing to note here is that these gradients are over two different parameters. So the gradient of q is with respect to the actions, such that the action A equals mu of s of t. So what this tells you is that q is actually a function not just of the state, but is intimately related to that policy mu. So it's not an action chosen according to an argmax, for instance. It's an action chosen according to the output of the other network. And for the update of mu, it's just the gradient with respect to the weights, which you would kind of expect. So they talk about another algorithm, NFQCA. I don't know what that is, honestly. Mini batch version, blah, blah, blah. Our contribution here is to provide modifications to DPG inspired by the success of DQN, which allow it to use neural network function approximators to learn in large state and action spaces online. We call it DDPG, very creative. As they say again, we use a replay buffer to address the issues of correlations between samples generated on subsequent steps within an episode. Finite size cache size R, transition sample from the environment. So we know all of this. So if you don't know all of it, what you need to know here is that you have state, action, reward, and then new state transitions. So what this tells the agent is started in some state S, took some action, received some reward, and ended up in some new state. Why is that important? It's important because in anything that isn't dynamic programming, you're really trying to learn the state probability distributions. You're trying to learn the probability of going from one state to another and receiving some reward along the way. If you knew all of those beforehand, then you could just simply solve a very, very large set of equations, for that matter, to arrive at the optimal solution, right? If you knew all those transitions, you say, okay, if I start in this state and take some action, I'm going to end up in some other state with certainty. Then you'd say, well, what's the most advantageous state? What state is going to give me the largest reward? And so you could kind of construct some sort of algorithm for traversing that set of equations to maximize your reward over time. Now, of course, you often don't know that, and that's the point of the replay buffer, is to learn that through experience and interacting with the environment. And it says when the replay buffer was full, oldest samples were discarded. Okay, that makes sense. It's finite size. It doesn't grow indefinitely. At each time step, actor and critic are updated by sampling a mini batch uniformly from the buffer. So it operates exactly according to Q-learning. It does a uniform sampling, random sampling of the buffer, and uses that to update the actor and critic networks. What's critical here is that combining this statement with the topic of the previous paragraph is that when we write our replay buffer class, it must sample states at random. So what that means is you don't want to sample a sequence of subsequent steps. And the reason is that there are large correlations between those steps, right, as you might imagine. And those correlations can cause you to get trapped in little nooks and crannies of parameter space and really cause your algorithm to go wonky. So you want to sample that uniformly so that way you're sampling across many, many different episodes to get a really good idea of the, I guess, the breadth of the parameter space, to use kind of loose language. And then it says directly implementing Q-learning with neural networks prove to be unstable in many environments. And they're going to talk about using the target network, okay, but modified for actor critic using soft target updates rather than directly copying the weights. So in Q-learning, we directly copy the weights from the evaluation to the target network. Here it says we create a copy of the actor and critic networks, Q prime and mu prime, respectively, that are used for calculating the target values. The weights of these target networks are then updated by having them slowly track the learned networks. Theta prime goes to theta times tau plus 1 minus tau times theta prime, with tau much, much less than 1. This means that the target values are constrained to change slowly, greatly improving the stability of learning. Okay, so this is our next little nugget. So let's head it over to the paper and to our text editor and make note of that. What we read was that we have two, not in caps, we don't want to shout. We have two networks, target networks. Sorry, we have two actor and two critic networks, a target for each. Updates are soft according to theta equals tau times theta plus 1 minus tau times theta prime. So, sorry, this should be theta prime. So this is the update rule for the parameters of our target networks. And we have two target networks, one for the actor and one for the critic. So we have a total of 4 deep neural networks. And so this is why the algorithm runs so slowly. Even on my beastly rig, it runs quite slowly, even in the lunar lander and continuous lunar lander environment. I've done the bipedal walker, and it took about 20,000 games to get something that approximates a decent score. So this is a very, very slow algorithm. And that 20,000 games took, I think, about a day to run. So quite slow, but nonetheless quite powerful. It's the only method we have so far of implementing deep reinforcement learning in continuous control environments. So hey, beggars can't be choosers, right? But we know, just to recap, that we're going to use 4 networks, 2 that are on policy and 2 off policy, and the updates are going to be soft with tau much less than 1. If you're not familiar with mathematics, this double less than or double greater than sign means much less than or much greater than, respectively. So what that means is that tau is going to be of order 0.01 or smaller, right? 0.1 isn't much smaller, that's kind of smaller. 0.01 I would consider much smaller. We'll see in the details, we'll see what value they use, but you should know that it's of order 0.01 or smaller. And the reason they do this is to allow the updates to happen very slowly to get good conversions, as they said in the paper. So let's head back to the paper and see what other nuggets we can glean before getting to the outline of the algorithm. And then in the very next sentence they say, this simple change moves the relative unstable problem of learning the action value function closer to the case of supervised learning, a problem for which a robust solution exists. We found that having both the target mu prime and q prime was required to have stable targets yi in order to consistently train the critic without divergence. This may slow learning since the target networks delay the propagation of value estimates. However, in practice, we found this was always greatly outweighed by the stability of learning, and I found that as well. You don't get a whole lot of divergence, but it does take a while to train. Then they talk about learning in low-dimensional and higher-dimensional environments, and they do that to talk about the need for feature scaling. So one approach to the problem, which is the ranges of variations in parameters, right? So in different environments, like in the mountain car, you can go from plus minus 1.6, like minus 1.6 to 0.4, something like that, and the velocities are plus or minus 0.07. So you have a 2-order magnitude variation there in the parameters. That's kind of large even in that environment. And then when you compare that to other environments where you can have parameters that are much larger, on the order of hundreds, you can see that there's a pretty big issue with the scaling of the inputs to the neural network, which we know from our experience that neural networks are highly sensitive to the scaling between inputs. So it says their solution to that problem is to manually scale the features so they're in similar across environments and units. And they do that by using batch normalization. And it says this technique normalizes each dimension across the samples in a mini batch to have unit mean and variance. And it also maintains a running average of the mean and variance used for normalization during testing, during exploration and evaluation. So in our case, training and testing are slightly different than in the case of supervised learning. So in supervised learning, you maintain different data sets or shuffled subsets of a single data set to do training and evaluation. And of course, in the evaluation phase, you perform no weight updates of the network. You just see how it does based on the training. In reinforcement learning, you can do something similar where you have a set number of games where you train the agent to achieve some set of results, and then you turn off the learning and allow it to just choose actions based upon whatever policy it learns. And if you're using batch normalization, in PyTorch in particular, there are significant differences in how batch normalization is used in the two different phases. So you have to be explicit in setting training or evaluation mode. In particular, in PyTorch, they don't track statistics in evaluation mode, which is why when we wrote the DDPG algorithm in PyTorch, we had to call the eval and train functions so often. Okay, so we've already established we'll need batch normalization, so everything's kind of starting to come together. We need a replay network, batch normalization. We need 4 networks, right? We need two each of a target of an actor and 2 each of a critic. So half of those are going to be used for on policy, and half of them are going to be used for off policy for the targets. And then it says, if you scroll down, a major challenge of learning in continuous action spaces is exploration. An advantage of off-policy algorithms such as DDPG is that we can treat the problem of exploration independently from the learning algorithm. We constructed an exploration policy mu prime by adding noise sampled from a noise process n to our actor policy. Okay, so right here it's telling us what basically the target actor function is. It's mu prime is basically mu plus some noise n. N can be chosen to suit the environment, as detailed in the supplementary materials we used in Ornstein-Uhlenbeck process to generate temporally correlated exploration for exploration efficiency and physical control problems with inertia. If you're not familiar with physics, inertia just means the tendency of stuff to stay in motion. It has to do with like environments that move, like the walkers, the cheetahs, stuff like that, the ants. Okay, so we've kind of got one other nugget to add to our text editor. Let's head back over there and write that down. Okay, so the target actor is just the evaluation, we'll call it that for lack of a better word, evaluation actor plus some noise process. They used Ornstein Uhlenbeck. I don't think I spelled that correctly. We'll need to look that up. That I've already looked it up. My background is in physics, so it made sense to me. It's basically a noise process that models the motion of Brownian particles, which are just particles that move around under the influence of their interaction with other particles in some type of medium, like a lossless medium, like a perfect fluid or something like that. And in the Ornstein-Uhlenbeck case, they are temporally correlated, meaning each time step is related to the time step prior to it. And I hadn't thought about it before, but that's probably important for the case of Markov decision processes, right? So in MDPs, the current state is only related to the prior state and the action taken. You don't need to know the full history of the environment. So I wonder if that was chosen that way, if there's some underlying physical reason for that. Just kind of a question occurs to me off the top of my head. I don't know the answer to that. If someone knows, hey, drop the answer in the comments. I would be very curious to see the answer. So we have enough nuggets here. So just to summarize, we need a replay buffer class. We'll also need a class for the noise, right? So we'll need a class for noise, a class for the replay buffer. we'll need a class for the target queue network, and we're going to use batch normalization. The policy will be deterministic, so what that means in practice is that the policy will output the actual actions instead of the probability of selecting the actions. So the policy will be limited by whatever the action space of the environment is, so we'll need some way of taking that into account. So deterministic policy means outputs the actual action instead of a probability. We'll need a way to bound the actions to the environment limits. And of course, these notes don't make it into the final code. These are just kind of things you think of as you are reading the paper. You would want to put all your questions here. I don't have questions since I've already implemented it, but this is kind of my thought process as I went through it the first time, as best as I can model it after having finished the problem. And you can also use a sheet of paper. There's some kind of magic about writing stuff down on paper, but we're going to use the code editor because I don't want to use an overhead projector to show you guys a friggin' sheet of paper. This isn't grade school here. So let's head back to the paper and take a look at the actual algorithm to get some real sense of what we're going to be implementing. The results really aren't super important to us yet. We will use that later on if we want to debug the model performance, but the fact that they express it relative to a planning algorithm makes it difficult, right? So scroll down to the data really quick. So they give another thing to note. I didn't talk about this earlier, but I guess now is a good time. Is the stipulations on this performance data. It says performance after training across all environments for at most 2.5 million steps. So I said earlier I had to train the bipedal walker for around 20,000 games. That's around I think that's around about 2.5 million steps or so. I think it was actually on 15,000 steps, so maybe around 3 million steps, something like that. We report both the average and best observed across 5 runs. So why would they use 5 runs? So if this was a super duper algorithm, and which none of them are, this isn't a slight on their algorithm, this isn't meant to be snarky or anything. What it tells us is that they had to use 5 runs because there is some element of chance involved. So one problem with deep learning is the problem of replicability, right? It's hard to replicate other people's results, particularly if you use system clocks as seeds for random number generators, right? Using the system clock to seed the random number generator guarantees that if you run the simulation at even a millisecond later, right, that you're going to get different results because you're going to be starting with different sets of parameters. Now, you will get qualitatively similar results, right? You'll be able to repeat the general idea of the experiments, but you won't get the exact same results. It's kind of it's an objection to the whole deep learning phenomenon. It makes it kind of not scientific, but whatever, it works, has enormous success. So we won't quibble about semantics or philosophical problems, but we just need to know for our purposes that even these people that invented the algorithm had to run it several times to get some idea of what was going to happen because the algorithm is inherently probabilistic, and so they report averages and best case scenarios. So that's another little tidbit, and they included results for both the low dimensional cases where you receive just a state vector from the environment as well as the pixel inputs. We won't be dealing with pixel inputs for this particular video, but maybe we'll get to them later. I'm trying to work on that as well. So these were the results, and the interesting tidbit here is that it's probabilistic. It's going to take 5 runs. So, okay, fine. Other than that, we don't really care about results for now. We'll take a look later, but that's not really our concern at the moment. So now we have a series of questions. We have answers to all those questions. We know how we're going to handle the explore-exploit dilemma. We know the purpose of the target networks. We know how we're going to handle the noise. We know how we're going to handle the replay buffer. And we know what the policy actually is going to be. It's the actual actions the agent is going to take. So we know a whole bunch of stuff. So it's time to look at the algorithm and see how we fill in all the details. So randomly initialize a critic network and actor network with weights theta super q, theta super mu. So this is handled by whatever library you use. You don't have to manually initialize weights, but we do know from the supplemental materials that they do constrain these updates to be within, these initializations to be within some range. So put a note in the back of your mind that you're going to have to constrain these a little bit. And then it says initialize target network Q prime and mu prime with weights that are equal to the original network. So theta super Q prime gets initialized with theta super Q, and theta mu prime gets initialized with theta super mu. So we will be updating the weights right off the bat for the target networks with the evaluation networks. And initialize a replay buffer R. Now this is an interesting question. How do you initialize that replay buffer? So I've used a couple different methods. You can just initialize it with all zeros, and then if you do that, when you perform the learning, you want to make sure that you have a number of memories that are greater than or equal to the mini batch size of your training, so that way you're not sampling the same states more than once, right? If you have 64 memories in a batch that you want to sample, but you only have 10 memories in your replay buffer, then you're going to sample, or let's say 16 memories, and you're going to sample each of those memories 4 times, right? So then that's no good. So the question becomes, if you initialize a replay buffer with zeros, then you have to make sure that you don't learn until you exit the warm-up period, where the warm-up period is just a number of steps equal to your replay buffer, your buffer sample size. Or you can initialize it with the actual environmental play. Now this takes quite a long time. The replay buffers are order 1 million, so if you let the algorithm take 1 million steps at random, then it's going to take a long time. I always use zeros, and then just wait until the agent fills up the mini batch size of memories. Just a minor detail there. Then it says, for some number of episodes do, so a for loop, initialize a random process N for action exploration. So this is something, now reading it, I actually made a little bit of a mistake. So in my previous implementation, I didn't reset the noise process at the top of every episode. So it's explicit here. I must have missed that line. And I've looked at other people's code. Some do, some don't. But it worked within, how many episodes was it? Within under 1,000 episodes, the agent managed to beat the continuous lunar lander environment. So is that critical? Maybe not. And I think I mentioned that in the video. Receive your initial state observation S1. So for each step of the episode, t equals 1 to capital T do. Select the action A sub t equals mu, the policy, plus n sub t according to the current policy and exploration noise. Okay, so that's straightforward. Just feed the state forward. What does that mean? It means feed the state forward through the network, receive the vector output of the action, and add some noise to it. Okay. Execute that action and observe reward and new state. Simple. Store that transition, the old state, action, reward, and new state in your replay buffer R. Okay, that's straightforward. Each time step, sample a random mini batch of n transitions from the replay buffer. And then you want to use that set of transitions to set y sub I equals, so I is, sorry, having difficulties here. So I is each step of that, is each element of that mini batch of transitions. So you want to basically loop over that set or do a vectorized implementation. Looping is more straightforward. That's what I do. I always opt for the most straightforward and not necessarily most efficient way of doing things the first time through, because you want to get it working first and worry about implementation, efficiency later. So set y sub I equals r sub I plus gamma, where gamma is your discount factor, times q prime of the new state s sub I plus 1 times where the action is chosen according to mu prime, given some weights theta super mu prime and theta super q prime. So what's important here is that, and this isn't immediately clear if you're reading this for the first time, this is a very important detail. So it's the action must be chosen according to the target actor network. So you actually have Q as a function of the state as well as the output of another network. That's very important. Update the critic by minimizing the loss, basically a weighted average of that y sub I minus the output from the actual Q network, where the a sub i's are from the the actions you actually took during the course of the episode. So this A sub I is from the replay buffer, and these actions, right, are chosen according to the target actor network. So for each learning step, you're going to have to do a feed forward pass of not just this target cue network, but also the target actor network, as well as the evaluation critic network. I hope I said that right. So the feed forward pass of the target critic network, as well as the target actor network, and the evaluation critic network as well. And then it says, update the actor policy using the sample policy gradient. Now, this is the hardest step in the whole thing. This is the most confusing part. So it says the gradient is equal to 1 over n times the sum. So a mean, basically, whenever you see 1 over n times the sum, that's a mean. The gradient with respect to actions of Q, where the actions are chosen according to the policy mu of the current states S, times the gradient with respect to the weights of mu, where you just input the set of states. Okay, so that'll be a little bit tricky to implement. And this is part of the reason I chose Tensorflow for this particular video, is because Tensorflow allows us to calculate gradients explicitly. In PyTorch, you may have noticed that all I did was set Q to be a function of the current state as well as the actor network. And so I allowed PyTorch to handle the chain rule. This is effectively a chain rule. So let's scroll up a little bit to look at that, because this kind of gave me pause the first 10 times I read it. So this is the hardest part to implement. If you scroll up, you see that this exact same expression appears here, right? And this is in reference to this. So it's a gradient with respect to the weights, theta super mu, of Q of S and A, such that you're choosing an action A according to the policy mu. So really what this is the chain rule. So it's the this gradient is proportional to a gradient of this quantity times a gradient of the other quantity. It's just a chain rule from calculus. So in the PyTorch paper, we implemented this version, and these are equivalent. It's perfectly valid to do one or the other. So in PyTorch, we did this version. Today, we're going to do this particular version. So that's good to know. All right. So next step. On each time step, you want to update the target networks according to this soft update rule. So theta super q prime gets updated as tau times theta super q plus 1 minus tau theta super q prime, and likewise for theta super mu prime. And then just end the two loops. So in practice, this looks very, very simple. But what do we know off the bat? We need a class for our replay network. We need a class for our noise process. We need a class for the actor and a class for the critic. Now, you could think that perhaps they're the same, but when you look at the details, which we're going to get to in a minute, you realize you need two separate classes. So you need at least one class to handle the deep neural networks. So you have at least three classes, and I always add in an agent class on top as kind of an interface between the environment and the deep neural networks. So that's 4. And we're going to end up with 5, but that's 4 right off the bat. So now that we know the algorithm, let's take a look at the supplemental details, supplemental information to see precisely the architectures and parameters used. So we scroll down. So here are the experimental details. These Atom for learning the neural network parameters with a learning rate of 10 to the minus 4 and 10 to the minus 3 for the actor and critic respectively. So they tell us the learning rates, 10 to the minus 4, 10 to the minus 3 for actor critic. For Q, the critic, we included L2 weight decay of 10 to the minus 2 and used a discount factor of gamma 0.99. So that gamma is pretty typical, but this important thing is that for Q, and only Q, not mu, we included L2 weight decay of 10 to the minus 2 and used a discount factor of gamma of 0.99. That's an important detail. For the soft target updates, we use tau equals 0.001, so 1 part in 1,000. That is indeed very, very small. Okay, fine. The neural networks use the rectified nonlinearity for all hidden layers. Okay. The final output layer of the actor was a tangent hyperbolic layer to bound the actions. Now, tan hyperbolic goes from -1 to +1. So in environments in which you have bounds of plus or minus 2, let's say, you're going to need a multiplicative factor. So that's just something to keep in mind. The low dimensional networks, but that doesn't that doesn't impact the tangent hyperbolic. It just means there's a multiplicative factor and they're related to your environment. The low-dimensional networks had 2 hidden layers with 400 and 300 units, respectively, about 130,000 parameters. Actions were not included until the second hidden layer of Q. So when you're calculating the critic function, Q, you aren't actually passing forward the action from the very beginning. You're including it as a separate input at the second hidden layer of Q. That's very important. That's a very important implementation detail. And this is when learning from pixels, we use 3 convolution layers, which we don't need to know right now. We're not using pixels yet. Followed by 2 fully connected layers. The final layer weights and biases of both the actor and critic were initialized from a uniform distribution of plus or minus 3 by 10 to the minus 3 for the low-dimensional case. This was to ensure that the initial outputs for the policy and value estimates were near 0. The other layers were initialized from uniform distribution of plus or minus 1 over square root of f, where f is the fan-in of the layer. Fan-in is just the number of input units. And the other layer, oh, I already read that. The actions were not included until the fully connected layers. That's for the convolutional case. So here, right now, I'm experiencing some confusion reading this. So, it says the other layers were initialized from uniform distributions related to the fan-in. The actions were not included until the fully connected layers. So I'm guessing, since they're talking about fully connected layers, they're talking about the pixel case, right? Because otherwise they're all fully connected. You know, it wouldn't make sense to specify fully connected layers. So this gives me a little bit of confusion. Is this statement referring to, the way I initially interpreted it, it is referring to both cases for the state vector and pixel case. But whatever. I'm going to interpret it that way because it seemed to work. But there's ambiguity there, and this is kind of an example of how reading papers can be a little bit confusing at times because the wording isn't always clear. Maybe I'm just tired. Maybe I've been rambling for about 50 minutes and my brain's turning to mush. That's quite probable, actually. But anyway, we trained with mini-match sizes of 64 for the low-dimensional problems and 16 on pixels with a replay buffer of 10 to the 6. For the exploration noise process, we use temporally correlated noise in order to explore well in physical environments that add momentum. Ornstein-Uhlenbeck process with theta equals 0.15 and sigma equals 0.2. And it tells you what it does. All well and good. Okay, so these are the implementation details. We need 400 units and 300 units for our hidden layers. Atom optimizer, 10 to the minus 4 for the actor, 10 to the minus 3 for the critic. For the critic, we need an L2 weight decay of 10 to the minus 2, discount factor of gamma 0.99. And for the soft update factor, we need 0.001. And we need updates, we need initializations that are proportional to the 1 over the square root of fan-in for the lower layers and plus minus 0.003, 003 for the final output layers of our fully connected networks. Okay, so that's a lot of details. We have everything we need to start implementing the paper. That only took us about 50 minutes, which is much shorter than when I read it. It took me quite a while. So let's head back up to the algorithm here, and we'll keep that up as reference for the remainder of the video because that's quite critical. So let's go ahead and head back to our code editor and start coding this up. We'll start with the easy stuff first. So let's start coding, and we will start with probably one of the most confusing aspects of the problem of the Ornstein-Uhlenbeck action noise. Now, you can go ahead and do a Google search for it, and you'll find a Wikipedia article that talks a lot about the physical processes behind it, a lot of mathematical derivations, and that's not particularly helpful. So if you want to be a physicist, I invite you to read that and check it out. It's got some pretty cool stuff. It took me back to my grad school days, but we have a different mission in mind for the moment. The mission now is to find a code implementation of this that we can use in our problem. So if you then do a Google search for Ornstein-Uhlenbeck GitHub, as in you want to find someone's GitHub example for it, you end up with a nice example from the OpenAI baseline library that shows you the precise form of it. So let me show you that 1 second. So you can see it here in the GitHub. There is a whole class for this right here that I've highlighted, and this looks to do precisely what we want. It has previous plus a delta term and a dt term, so it looks like it's going to create correlations through this x previous term. There's a reset function to reset the noise, which we may want to use. And there's this representation, which we'll probably skip because we know what we're doing and it's not really critical for this particular application, though it would be nice if you were writing a library, as these guys were, so they included the representation method. So let's go ahead and code that up in the editor, and that will tackle our first class. So I'm going to leave the notes up there for now. They do no harm. They're just comments at the top of the file. So the first thing we'll need is to import numpy as np. We know we can go ahead and start and say import TensorFlow as tf. We're going to need TensorFlow. We may need something like OS to handle model saving, so we can go ahead and import that as well. Just a fun fact, it is considered good practice to import your system level packages first, and followed by your library packages second in numerical order, followed by your own personal code in numerical order. So that's the imports that we need to start. Let's go ahead and code up our class. We'll call it OU action noise, and that'll just be derived from the base object. So the initializer will take a mu, a sigma. Now they said they used a default value of, I believe, 0.15 and a theta of 0.2. A dt term, something like 1 by 10 to the minus 2, and our x naught we'll save as none. And again, if you have any doubts on that, just go check out the OpenAI baselines for it. Their implementation is probably correct, right? I'll give them the benefit of the doubt. So go ahead and save your parameters as usual. So we have a mu, a theta, a dt, a sigma, an x0, and we'll go ahead and call the reset function at the top. Now they override the call method, and what this does is it enables you to say noise equals OU action noise, and then when you want to get the noise, you would just say our noise equals noise. You can use the parentheses. That's what overriding call does. That's a good little tidbit to know. So we want to implement the equation that they gave us. It's self.x previous plus self.theta times mu minus x previous times self.dt plus sigma times numpy dot square root self.dt times numpy random normal with a size of mu, and set the x previous to the current value. That's how you create the temporal correlations and return the value of the noise. So we don't have a value for x previous, so we have to set that with the reset function, which takes no parameters. Self.x previous equals x naught if self.x naught is not none, else numpy zeros like self.mu. And that's it for the noise function. That's pretty straightforward. So that's all well and good. So we have one function down. So we've taken care of the noise. Sorry, we have one class down. We've taken care of the noise, and now we can move on to the replay buffer. So this will be something similar to what I've implemented in the past. There are many different implementations and ways of implementing this. Many people will use a built-in Python data structure called a DQ or a DEC. I think it's DQ is the pronunciation. Basically, it's a queue that you fill up over time, and that's perfectly valid. You can do that. There's no reason not to. I prefer using a set of arrays and using NumPy to facilitate that. The reason being that we can tightly control the data types of the stuff that we're saving. For this pendulum environment, it doesn't really matter, but as you get more involved in this field, you will see that you are saving stuff that has varying sizes. So if you're trying to save images, let's say, from one of the Atari libraries or a Mujoko environment or something like that, hope I pronounced that correctly, you'll see that this memory can explode quite quickly. You can eat into your RAM. So the ability to manipulate the underlying data type representation, whether you want to use single or double precision for either your floating point numbers or your integers, is critical to memory management, as well as taking advantage of some other optimizations for NVIDIA GPUs in the Turing class and above. So I always use the NumPy arrays because it's a clean implementation that allows manipulation of data types. You can use the DQ if you want. It's perfectly valid. So our separate class has its own initializer, of course. So we're going to want to pass in a maximum size, the input shape, and the number of actions, right? Because we have to store the state, action, reward, and new state tuples. We're also going to want to facilitate the use of the done flag, so we'll have an extra parameter in here. And the reason behind that is intimately related to how the Bellman equation is calculated. It took me a second to think of that. At the end of the episode, the agent receives no further rewards, and so the expected future reward, the discounted future reward, if you will, is identically 0. So you have to multiply the reward for the next state by 0 if that next state follows the terminal state. If your current state is terminal, then the next state is following the terminal state, so you don't want to take into account anything from that, the expected future rewards, because they're identically 0. So we need a done flag, is all I wanted to say. So we save our parameters. We don't even need to save that. We can say self.mem counter equals 0, and that'll keep track of the position of our most recently saved memory. State memory, an array of numpy zeros, mem size by input shape, new state memory. Same deal, you know. It's just totally the same. Good grief. Okay, so now we have the, let's say, action memory, and that's numpy zeros, self.mem size by self.n actions. We didn't save n actions, did we? So we'll just call it n actions. We have the reward memory, and that's just a scalar value, so that only gets shape self mem size. We also need the terminal memory. Terminal memory, and that'll be shape self.mem size. And I have it numpy float 32. If I recall correctly, that is due to the data types in the PyTorch implementation. It's probably not necessary here in the TensorFlow implementation, but I left it the same way just to be consistent. It doesn't hurt anything. So next we need a function to store a current transition. So that'll take a state, action, reward, new state, and a done flag as input. So the index of where we want to store that memory is the memory counter modulus the mem size. So for any mem counter less than mem size, this just returns mem counter. For anything larger than mem size, it just wraps around. So if you have 1,000,000 memories all the way up from 0 to 999,999, it will be that number, and then once it's 1,000,000, it wraps back around to 0, and then 1 and 2 and so on and so forth. And so that way you're overriding memories at the earliest part of the array with the newest memories, precisely as they describe in the paper. If you're using the DQ method, then I believe you would just pop it off of the left, I believe. Now, don't quote me because I haven't really used that implementation, but from what I've read, that's how it operates. New state memory, subindex equals state underscore reward memory equals subindex reward as action memory. Now keep in mind that the actions in this case are arrays themselves, so it's an array of arrays. Just keep that in the back of your mind so that you can visualize the problem we're trying to solve here. Next up we have the terminal memory. Now a little twist here is that we want this to be 1 minus int of done. So done is either true or false, so you don't want to count the rewards after the episode has ended. So when done is true, you want to multiply by 0. So 1 minus int of true is 1 minus 1, which is 0. And when it's not over, it's 1 minus 0, which is just 1. So that's precisely the behavior we want. And finally, you want to increment mem counter by 1 every time you store new memory. Next, we need a function to sample our buffer, and we want to pass in a batch size. Alternatively, you could make batch size a member variable of this class. It's not really a big deal. I just did it this way for whatever reason I chose to do it that way. So what we want to do is we want to find the minimum either. So let's back up for a second. So what we want is to sample the memories from either the 0th position all the way up to the most filled memory, the last filled memory. So if you have less than the max memory, you want to go from 0 to mem counter. Otherwise, you want to sample anywhere in that whole interval. So max mem equals the minimum of either mem counter or mem size. And the reason you don't want to just use mem counter is that mem counter goes larger than mem size. So if you try to tell it to select something from the range mem counter when mem counter is greater than mem size, you'll end up trying to access elements of the array that aren't there, and it'll throw an error. So that's why you need this step. Next, you want to take a random choice of from 0 to max mem of size batch size. So then you just want to gather those states from the respective arrays, like so. I forgot the self, of course. New states, actions, rewards, and call it terminal batch. I believe that's everything. And you want to return the states, actions, rewards, new states, and terminal. Okay, so now we are done with the replay buffer class. So that's actually pretty straightforward. And if you've seen some of my other videos on deep Q learning, then you've seen pretty much the same implementation. I just typically kept it in the agent class then. I'm kind of refining my approach, getting more sophisticated over time, so it makes sense to stick it in its own class. So we're already like 40% of the way there. We got 5 classes in total, so that's good news. So next up, we have to contend with the actor and critic networks. So we'll go ahead and start with the actor, and from there, keep in mind that we have 2 actor networks, and we're going to have to contend with some of the peculiarities and way TensorFlow likes to do stuff. So let's get started. The actor, and of course in TensorFlow you don't derive from any particular class, where in PyTorch you would derive from nn.module. Don't know what I'm doing there. Def init. So we'll need a learning rate, number of actions, a name, and the name is there to distinguish the regular actor network from the target actor network. Input dims. We're going to want to pass it a session, so TensorFlow has the construct of the session, which houses the graph and all the variables and parameters and stuff like that. You can have each class having its own session, but it's more tidy to pass in a single session to each of the classes. Number of dimensions for the first fully connected layers, so of course that should be 400. If we're going to implement the paper precisely, FC2dims is 300. An action bound, a batch size, that defaults to 64. A checkpoint directory, and the purpose of that is to save our model. And in the case of the pendulum, it doesn't really matter because it's so quick to run, but in general you want a way of saving these models because it can take a long time to run. So we'll save our learning rate, number of actions, and all of the parameters we passed in. Dot FC1 dims. And the purpose of this action bound is to accommodate environments where the action is either greater than plus or minus -1. So if you can go from plus or minus 2, then the tangent hyperbolic is only going to sample like half your range, right, from plus minus 1. And so you want to have an action bound in there as a multiplicative factor to make sure that you can sample the full range of actions available to your agent. And we need to say that checkpoint dir. And finally, we want to call a build network function. Well, it's not final, but we'll call the build network function. Next up, since we have to do the soft cloning, the soft update rule for the target actor class and target critic, then we know that we have to find a way of keeping track of the parameters in each network. So we're going to keep track of them here in the variable params. And it's tensorflow.trainable variables with a scope of self.name. So we have a single session, a single graph, and you're going to have multiple deep neural networks within that graph. We don't want to update the critic network when we're trying to do the actor network and vice versa, right? We want those to be independent. And so we scope them with their own name so that TensorFlow knows, hey, this is a totally different set of parameters from this one. And that'll aid in copying stuff later, and it'll also make sure that everything is nice and tidy. And the scope is what facilitates that. We'll also need a saver object to save the model. Let's make a checkpoint file, and that's where we use OS, and that will clone into checkpoint dir and the name plus underscore ddpg.checkpoint. So this will automatically scope the save files for us, so that way we don't confuse the parameters for the target actor and actor, or critic and target critic, or even actor and critic for that matter. Very important. So we're going to have to calculate some gradients, and we're going to do that by hand. So we're going to need a series of functions that will facilitate that. And the first of which is the unnormalized actor gradients. And that is given my tensorflow.gradients, self.mu, self.params, and minus self.action gradient. So we're going to calculate, so mu will be the mu from the paper, the actual actions of the agent. Params are our network parameters, and this action gradient. So let's go back to the paper for a second so we can get some idea of what I'm talking about here. So if we look at the algorithm, we can see that we're going to need these gradients of the critic function with respect to the actions taken. We're also going to need the gradient of the actual mu with respect to the weights of the network. So we're passing into TensorFlow gradients this function mu, the parameters to get the gradient with respect to those parameters, and then we're going to have to calculate the gradient of the critic with respect to the actions taken. So we'll have to calculate this later. That's a placeholder. That's the minus self.action gradient, and we're going to calculate that in the learning function. But that's where all of that comes from. So now let's go back to the code editor and continue. So that's our unnormalized actor gradients, and unnormalized is just because we're going to take 1 over the sum, 1 over n times the sum. We need a function for performing that normalization. So the actor gradients has to be, this parameter has to be a list, so we cast it as a list, and we're just going to map a lambda function, lambda x, tf.div x, and batch size. No big deal there. So optimize is our optimization step. And of course, that's the atom optimizer. We want to optimize with a learning rate of self.learning rate, and we want to apply gradients. So typically you would use .minimize loss, but in this case we're calculating our gradients manually, so we need to apply those gradients. And what do we want to apply? We want to apply the actor gradients to the params. And I would encourage you to go look at the TensorFlow code for all of these. The video is getting a little bit long. We're already up to like an hour and 10, 20 minutes, something like that. So I'm not going to go through all the documentation for TensorFlow. Feel free to look that up. I had to when I was building this out. So next up, we need to build our network. So This is how we're going to handle the scoping. tf.variable underscore scope self.name, so that way every network gets its own scope. We need a placeholder for the input. That'll be a 32-bit floating number. Shape of none, which is batch size. Input dims, dioms, that won't work. Let's put this on its own line. And we're going to give it a name. It's not critical. The name parameter is just for debugging. If something goes wrong, then you can kind of trace where it went wrong. Makes life a little bit easier. The action gradient is also a placeholder. That is what we're going to calculate in the learn function for the agent. And that gets a shape of none by n actions. So it'll be the gradient of q with respect to each action. So it has number of dimensions of actions. And so those are our two placeholder variables. Now we get to construct the actual network. So let's handle the initialization first. So f1 is the fan in. It's 1 divided by numpy square root fc1 dims. And our dense one, tf layers dot dense, and that takes self.input as input with self.fc1 dims as units. Our kernel initializer equals random, I forgot an import, it's random uniform 1 second minus f1 to f1, and the bias initializer kernel, no that's not right, kernel bias initializer random uniform minus f1 to f1. That gets 2 parentheses. So we have to come back up to our imports. Import Tensorflow dot initializers. No. So we have to come back up here and say from Tensorflow dot initializers import random uniform, and now we're good to go. Let's come back down here. We have dense 1. Now we want to do the batch normalization. So batch 1 equals tf layers batch normalization dense 1, and that doesn't get initialized. So now let's activate our first layer, and that's just the ReLU activation of the batch normed. Now it is an open debate from what I've read online about whether or not you should do the activation before or after the batch normalization. I'm in the camp of doing it after the activation after the batch norm. That's because the ReLU activation function, at least in the case of ReLU, so in ReLU you lop off everything lower than 0, so your statistics might get skewed to be positive instead of maybe they're 0, maybe they're negative, who knows. So I think the batch norm is probably best before the activation, and indeed this works out. This is something you can play with, so go ahead and fork this repo and play around with it and see how much of a difference it makes for you. Maybe I missed something when I tried to do it the other way. It's entirely possible I miss stuff all the time. So you know, it's something you can improve upon. That's how I chose to do it. And it seems to work, and who knows, maybe other implementations work as well. So now let's add some space. So f2 is 1 over square root fc2 dims. Dense 2 is similar. That takes layer 1 activation as input with fc2 dims. We don't need that. I'm going to come up here and copy this. There we go, except we have to change f1 to f2. Perfect. Then we have batch 2, and that takes dense 2 as input. Layer 2 activation. Batch 2. Now finally we have the output layer, which is the actual policy of our agent, the deterministic policy, of course. And from the paper that gets initialized with the value of 0.003. And we're going to call this mu. And that gets layer 2 activation as input, and that needs n actions as the number of output units. What's our activation? That is tangent hyperbolic, tanh. And I will go ahead and copy the initializers here. Of course, that gets F3, not F2. Perfect. Can I tab that? I can. Okay. So that is mu. And then we want to take into account the fact that our environment may very well require actions that have values plus greater than plus or minus 1. So self.mu is tf.multiply with mu and the action bound. And action bound will be, something like 2. It needs to be positive so that way you don't flip the actions. But that's pretty straightforward. So now we've built our network. Next thing we need is a way of getting the actual actions out of the network. So we have a prediction function that takes some inputs, and you want to return self.ses.run self.mu with a feed dictionary of self.input and pass in inputs. That's all that is there is to doing the feed forward. Kind of an interesting contrast to how PyTorch does it with the explicit construction of the feed forward function. This just runs the session on this and then goes back and finds all the associations between the respective variables. Nice and simple. Now we need a function to train, and that'll take inputs and gradients. This is what will perform the actual backpropagation through the network. And you want to run self.optimize, that's our function that accommodates learning, with a feed dictionary of inputs, and self.action gradients. So that is also reasonably straightforward. So, let's format that a little bit better. All right, so that is our training function. Next, we need 2 functions to accommodate the loading and the saving of the model. So define save checkpoint, print then you want to say self.saver.save, very creative. You want to save the current session to the checkpoint file, and the load checkpoint function is the same thing, just in reverse. So here we want to print loading checkpoint self.saver.restore.session and the checkpoint file. So that will you can only call this after instantiating the agent, so it will have a default session with some initialized values, and you want to load the variables from the checkpoint file into that checkpoint. And that is it for the actor class. This is reasonably straightforward. The only real mojo here is the actor gradients, and this is just 2 functions that accommodate the fact that we're going to manually calculate the gradient of the critic with respect to the actions taken. So let's go ahead and do the critic class next. That is also very similar. So that again derives from the base object, gets an initializer, and it's pretty much the same number of actions, a name, input dims, a session, SC1 dims, SC2 dims, a batch size will default to 64, and a checkpoint dir will default to this. Just a note, you have to do a make dir on this temp/DDPG first, otherwise it'll bark at you. Not a big deal, just something to be aware of. Since it's identical, let's go ahead and copy a good chunk of this stuff here. What exactly is the same? All of this. Now we need the checkpoint file. Let's grab that. Control C, come down here, Control V, voila, it is all the same. So very straightforward. Nothing too magical about that. So now let's handle the optimizer. Because we've already called the function to build our network, we can define our optimizer. So self.optimize tftrain.atom optimizer, and we're going to minimize the loss, which we will calculate in the build network function. And we also need the function to actually calculate the gradients of Q with respect to A. So we have self.action gradients, self.q, and actions. Let's build our network with TF variable scope self.name. So now we need our placeholders again. We need self.input placeholder float 32. We need a shape none by input dims. Now, if you're not too familiar with TensorFlow, specifying none in the first dimension tells TensorFlow you're going to have some type of batch of inputs, and you don't know what that batch size will be beforehand, so just expect anything. And let's delete that, say, oh, we need a comma for sure, and say name equals inputs. Here we go. Did I forget a comma up here? Let's just make sure. I did not. Okay. So we also need the actions, because remember we only take into account the actions on the second hidden layer of the Critic neural network. I have float 342, shape none by and actions, name of actions. Now, much like with Q-learning, we have a target value. Let me just go back to the paper really quick and show you what that precisely will be. So that target value will be this quantity here, and we will calculate that in the learning function as we get to the agent class. So let's go back to the code editor and finish this up. So Q-target is just another placeholder, and that's a floating point number. None by 1. It's a scalar, so it is shape batch size by 1, and we will call it targets. Okay, so now we have a pretty similar setup to the actor network. So let's go ahead and come up here and copy this. No, not all of that, just this, and come back down here. So F1 we recognize that's just the fan in. We have a dense layer for the inputs, and we want to initialize that with a random number. Pretty straightforward. Then we can come up to F2 and copy that as well. Sorry, the second layers. It'll be a little bit different, but we'll handle that momentarily. So now F2, the layer 2 is pretty similar. The only real difference is that we want to get rid of that activation. And the reason we want to get rid of that activation is because after we do the batch norm, we have to take into account the actions. So we need another layer. So action in, TF layers, dense. It's going to take in self.actions, which we'll pass in from the learning function. And that's going to output FC2 dims with a ReLU activation. So then our state actions will be the addition of the batch 2 and the action in, and then we want to go ahead and activate that. Okay, so this is something else I pointed out in my PyTorch video, where this is a point of debate with the way I've implemented this. I've done it a couple different ways. I've done the different variations, and this is what I found to work. I'm doing a double activation here. So I'm activating the ReLU. I'm doing the ReLU activation on the actions in, or on the output of that dense layer, and then I'm activating the sum. Now, the ReLU function is non-commutative with respect to the addition function, so the ReLU of the sum is different than the sum of the ReLUs, and you can prove that to yourself on a sheet of paper. But it's debatable on whether or not the way I've done it is correct. It seems to work, so I'm going to stick with it for now. Again, fork it, clone it, change it up, see how it works. and improve it for me. That would be fantastic. Then make a pull request and I'll disseminate that to the community. So we have our state actions. Now we need to calculate the actual output of the layer, and an F3 is our uniform initializer for our final layer, which is self.q. Self.layers.dense, that takes state actions as input, outputs a single unit, and we have the kernel initializers and bias initializers similar to up here. Let's paste that. There we go. That's a little bit better. Still got a whole bunch of white space there. All right. So we are missing one thing, and that one thing is the regularizer. So as I said in the paper, they have L2 regularization on the Critic. So we do that with kernel regularizer equals tf keras regularizers dot L2 with a value of 001. 01, sorry. So that is that for the Q, and notice that it outputs one unit, and it outputs a single unit because this is a scalar value. You want the value of the particular state action pair. Finally, we have the loss function, and that's just a mean squared error, Q target, and Q. So Q target is the placeholder up here, and that's what we'll pass in from the learn function from the agent, and self.q is the output of the deep neural network. Okay, so now similar to our Critic, we have a prediction function. It takes inputs and actions, and you want to return self.sess.run, self.q with a feed dictionary of self.input, inputs, and actions. Oops. Next, you need a training function, and that's slightly more complicated than the actor because that takes in the inputs, actions, and a target. And you want to return self.sess.run, self.optimize with a feed dictionary of self.input, inputs, self.actions, actions, and qtarget. The spacing on that's a little wonky, whatever, we'll leave it. That's a training function. Next, we need a function to get the action gradients, and that'll run that action gradients operation up above. So let's get that. Again, takes inputs and actions as input, and you want to return self.session.run, self.action gradients with its own feed dictionary equals self.input, inputs, and self.actions, actions. And then we also have the save and load checkpoint functions, which are identical to the actor, so let's just copy and paste those. There we go. So that is it for the Critic class. So now we have most of what we need. We have our noise, our replay buffer, our actor, and our Critic. Now all we need is our agent. Now the agent is what ties everything together. It handles the learning functionality. It'll house the noise, the memory, the replay buffer, as well as the 4 different deep neural networks. And that derives from the base object. The initializer is a little bit long, and that takes an alpha and a beta. These are the learning rates for the actor and Critic respectively. Recall from what we read in the paper, they use 0001 and 001 for both networks. We need input dims, tau, the environment. That's how we're going to get the action bounds. A gamma of 0.99 per the paper. In this case, we need number of actions equals 2. A mem size for our memory of 1 million. layer 1 size of 400, a layer 2 size of 300, and a batch size of 64. So of course we want to save all of our parameters. We'll need the memory, and that's just a replay buffer, max size, whoops, input dims, and number of actions. We will need a batch size. Here's where we're going to store the session, and this is so that we have a single session for all 4 networks. And I believe, don't quote me on this, but I tried it with an individual network an individual session for each network, and it was very unhappy when I was attempting to copy over parameters from one network to another. I figured there were some scoping issues, so I just simplified it by having a single session. There's no real reason that I can think of to have more than one. And that is an actor that gets alpha number of actions. The name is just actor. Input dims, the session, layer 1 size, layer 2 size, action space dot high, and that's our action bounds, the action space dot high. Next we have a critic that gets beta and actions. Its name is just critic. Input dims, self.session, layer 1 size, layer 2 size, and we don't pass in anything about the environment there. So now we can just copy these, and instead of actor, it is target actor. And let's go ahead and clean up and be consistent with our pet-bait style guides. Always important. That actually makes you stand out. I've worked on projects where the manager was quite happy to see that I had a somewhat strict adherence to it. Just something to take note of. So then we have a target critic as well. And we will clean up this. And so that is all 4 of our deep neural networks. That's pretty straightforward. So now we need noise. That's an OU action noise with mu equals numpy zeros in the shape and actions. So now we need operations to perform the soft updates. So the first time I tried it, I defined it as its own separate function. And that was a disaster. It was a disaster because it would get progressively slower at each soft update. And I don't quite know the reason for that. I just know that that's what happened. And so when I moved it into the initializer and defined one operation, I'm guessing it's because it adds, every time you call it, it probably adds something to the graph, so that adds overhead to the calculation. That's my guess. I don't know if that's accurate. It's just kind of how I reasoned it. But anyway, let's go ahead and define our update operations here. So what we want to do is iterate over our target critic parameters and call the assignment operation. What do we want to assign? We want to assign the product of critic params and self.tal plus gf.multiply self.target critic param sub I times and no, that should be a comma and 1 minus self.tal. So we get 2. Let's hit do that, and that is a list comprehension for I in range length of target critic dot params. I guess that. We don't need that. I don't believe. No. So then we have a similar operation for the actor. We just want to swap actor and critic. Target actor. Self dot actor actor dot params I did the same thing here, didn't I? Target actor, and up here dot params. Okay, target actor, and then target actor. There. So now we have our soft update operations according to the paper. Finally, we have constructed all of the graphs, for the whole 4 networks. So we have to initialize our variables. Self.session.run, tf global variables initializer. You can't really run anything without initializing it. And as per the paper at the very beginning, we want to update the network parameters. At the beginning, we want to pass in we want the target networks to get updated with the full value of the the evaluation networks, and so I'm passing in a parameter of first equals true. So since it's confusing, let's do that function first. Update network parameters. First will default to false. So if first, we need to say old tau equals self.tau. I need to save the old value of tau to set it again so that I can reset it. Self.tau equals 1, and say self.target critic.session.run update critic self.target actor.session.run self.update actor. And as I recall, this is important which session you use to run the update, although maybe not since I'm using only one session. If you want to play around with it, go ahead. And then go ahead and reset the tau to the old value because you only want to do this particular update where you update the target network with the original network full values on the first term, on the first go through. Otherwise, just go ahead and run the update function. Boom. So next we need a way of storing transitions. Self, state, action, reward, new state, and done. So self.memory.store transition. We want to store all this stuff. This is just an interface from one class to another. You know, this may or may not be great computer science practice, but it works. Next, we want a way of choosing an action, and that should take a state as input. Since we have defined the input variable to be shape batch size by n actions, you want to reshape the state to be 1 by, it should be 1 by the observation space. New access all, and that's because we have the come up here for the actor network. Just so we're clear, it is because this has shape none by input dims. So if you just pass in the observation vector that has shape input dims, and it's going to get uppity with you. So you just have to reshape it because you're only passing in a single observation to determine what action to take. So mu actor.predict state noise equals self.noise, mu prime equals mu plus noise. Return sub-0, so this returns a tuple, so you want the 0th element. So now we have the learning function, and of course this is where all the magic happens. So if you have not filled up the memory, then you want to go ahead and bail out. Otherwise, you want to go ahead and sample your memory. Self.memory.sample buffer batch size. So next we need to do the update from the paper. So let's go back to the paper and make sure we are clear on that. So we need to, we already sampled this, so we need to calculate this. And to do that, we're going to need the Q prime, the target critic network, as output, as well as the output from the target actor network. And then we'll use that to update the loss for the critic, and then we're going to need the output from the critic as well as from the actor network. So we need to basically pass states and actions through all four networks to get the training function, the learning function. So let's go ahead and head back to the code editor and do that. So our critic value for Q prime, so Q critic value underscore self.target critic.predict, and you want to pass in the new states, and you also want to pass in the actions that come from the target actor. New state. I need one extra parenthesis there. So then we want to calculate the y sub i's for the targets. So that's an empty list for j in range, self.batch size, target.append reward critic value underscore j times done sub j, and that's where the I kept harping on getting no rewards after the terminal state. That's where that comes from. When done is true, then it's 1 minus true, which is 0, so you're multiplying this quantity by 0, so you don't take into account the value of the next state, right, which is calculated up here. You only take into account the most recent reward, as you would want. So then we just want to reshape that target into something that's batch size by 1. That's to be consistent with our placeholders. And now we want to call the critic train function, right, because we have everything we need. We have the states, actions, and targets, with the states and actions from the replay buffer and the target from this calculation here. Very easy. Now we need to do the actor update. So the action outs self.actor.predict, we get the predictions from the actor for the states. Our grads, the gradients, get action, gradients, state, a-outs. That'll get the, remember, that'll do a feed forward and get the gradient of the critic with respect to the actions taken. And then you want to train the actor, state and grads, the gradients. It's a tuple, so you want to dereference it and get the 0th element. And then finally, you want to update network parameters. Woo. Okay, so that is it for the learn function. Now we have two other bookkeeping functions to handle, which is save models, and this will save all of our models. So self.actor.save checkpoint, self.targetActor save checkpoint, self.critic and a function to load models. Sounds like a dogfight out there. So we want to load checkpoints instead of saving them. Load checkpoints, load, and load. So that is it for the agent class. It only took about an hour, so we're up to about 2 hours for the video, so longest one yet. So this is an enormous amount of work. This is already 310 lines of code. If you've made it this far, congratulations. This is no mean feat. This took me, a couple weeks to hammer through, but we've gotten through it in a couple hours. So this is all there is to the implementation. Now we have to actually test it. So let's open up a new file and save that as main tensorflow.py. And what we want to do now is go ahead and test this out in the pendulum environment. I'll call it TensorFlow original. Import our agent. We need Jim. We need Do we need NumPy for this? Yes, we do. We don't need TensorFlow. From utils, import plot learning, and we don't need OS. So we will have a score history. You know what? I don't want to do it that way. Let's say if name equals main. Now we want to say env gym.make pendulum-v0 agent equals agent. It gets a learning rate of 0001, a beta of 01, and put dims 3 equals 3, tau 01, pass in our environment, batch size 64. I'm being verbose here, and it looks like when I ran this I actually used different layer sizes. Well, that's an issue for hyperparameter tuning. I just want to demonstrate that this works, and actions equals 1. So when I got good results for this, I actually used 800 by 600, and I cut these learning rates in half, but we'll go ahead and use the values from the paper. Sometimes I do hyperparameter tuning. Other thing we need to do is set our random seed. You know, we can just put it here, whatever. The reason we want to do this is for replicability, and I have yet to see an implementation of this where they don't set the random seed. And I've tried it without it, and you don't get very good sampling of your replay buffer. So this seems to be a critical step, and most implementations I've seen on GitHub do the same thing. So let's go ahead and play our episodes. Say 1,000 games. env.reset. We forgot our score history, of course. That's to keep track of the scores over the course of our games. Done is false. And the score for the episode is 0. So let's play the episode. Say act, agent.choose, action, takes obs as input, new state, reward, done, info equals env.step, act, agent.remember, obs, act, reward, new state, int done. I guess the int done really isn't necessary. We take care of that in the replay buffer class, but you know, doesn't hurt to be explicit. And then you want to we want to learn on each time step because this is a temporal difference method. Keep track of your score and set your old state to be the new state, so that way when you choose an action on the next step, you are using the most recent information. Finally, at the end of every episode, you want to append that score to the score history and print episode I score %.2f score 100 game average %.2f NumPy mean score history last 100 games minus 100 on one more, and at the end equals pendulum.png plot learning score history, file name, and a window of 100. The reason I chose a window of 100 is because many environments define solved as trailing 100 games over some amount. The pendulum doesn't actually have a solved amount, so what we get is actually on par with some of the best results people have on the leaderboard, so it looks like it does pretty well. So that is it for the main function. Let's go ahead and head to the terminal and see how many typos I made. Alright, here we are. Let's go ahead and run the main file. Invalid syntax. I have an extra parenthesis. I'm just going to delete that really quick. Run that. I have the star out of place. Let's go back to the code editor and handle that. So it looks like it is on line 95, which is here. All right, back to the terminal. Let's try it again. And it says line 198, invalid syntax. Oh, it's because it's a comma instead of a colon. All right, I'll fix that. Once more. All right, so that was close. So actor object has no attribute input dims, line 95. Okay, that's easy. Let's head back. So it's in line 95. Just means I forgot to save input dims. And that probably means I forgot it in the Critic as well, since I did a cut and paste. Yes, it does. All right, now we'll go back to the terminal. Hopefully that's the last one. All right, moment of truth. Critic takes one positional argument, but 7 were given. Good grief. Okay, 1 second. So that is, of course, in the agent function. So I have line 234. 1, 2, 3, 4, 5, 6, 7 parameters indeed. So Critic takes learning rate, number of actions, name, input dim, session. Interesting. 1, 2, 3, 4, 5, 6, 7. What have I done? Oh, that's why. It's class Critic, of course. All right, let's go back to the terminal and see what happens. Name action bound is not defined. And that is in the line 148. Okay. Line 148. That is in the Critic. That's because I don't need it there. Let's delete it. That was just for the actor. It's because I cut and pasted. Always dangerous. I tried to save a few keystrokes to save my hands and ended up wasting time instead. All right, let's go back to the terminal. All right. Actor has no attribute inputs. That is on line 126. Self.inputs, it's probably self.input. Yes. That's why I do the same thing here. Okay. Perfect. And it runs. So I'll let that run for a second, but I let it run for 1,000 games earlier, and this is the output I got. Now, keep in mind it's with slightly different parameters. The point here isn't that whether or not we can replicate the results, because we don't even know what the results really were, because they express it as a fraction of a fraction of the performance of a planning agent. So who knows what that really means. I did a little bit of hyperparameter tuning. All I did was double the number of input units and halve the learning rate. And I ended up with something that looks like this. So you can see it gets around 150 or so steps. It gets around 150 or so steps to solve. And if you check the leaderboards, it shows that that's actually a reasonable number. Some of the best environments only have 152 steps. Some of them do a little bit better. Sorry, best agents solve it in 152 steps or achieve a best score of 150 steps. But it's pretty reasonable. So the default implementation looks like it's very, very slow to learn. You can see how it's kind of starts out bad, gets worse, and then starts to get a little bit better. So that's pretty typical. You see this, oscillation in performance over time pretty frequently. But that is that. That is how you go from an paper to a full implementation in about 2 hours. Of course, it took me, many times that to get this set up for you guys. But I hope this is helpful. I'm going to milk this for all it's worth. This has been a tough project, so I'm going to present many, many more environments in the future. I may even do a video like this for PyTorch. I have yet to work on a Keras implementation for this, but there are many more DDPG videos to come, so subscribe to make sure you don't miss that. Leave a comment. Share this if you found it helpful. That helps me immensely. I would really appreciate it, and I'll see you all in the next video.